thanks to the organizer for giving me the opportunity to talk about this topic, possible origins of the galactic center excess with a spatial focus on dark matter. So as many of you know, there are many groups that have found an excess of gamma rays looking to the data of Fermi in the direction of the galactic center. And in particular, they found an excess by modeling the data with a galactic interstellar emission model, point at extended sources, an isotropic template, and the Fermi bubble emission. And if they include also a dark matter template, they find that there is an excess of gamma rays with a spectrum that is peaked around a few GeV of energy and with a spatial morphology that is roughly spherically symmetric. So the overview of my talk is presented in this slide. So I will present 3 papers, one that has been recently accepted, one submitted, and one under preparation. And so these 3 papers basically cover the overview of the talk. So in the first part, I will talk about the simulations. So we use simulations to investigate the sensitivity of the LAT for detecting the characteristics of the galactic center excess. In the second part, I will talk about the data analysis of 11 years of data, where we find the characteristics of the galactic center excess with very high precision, or at least with better precision than in the past for some observables. And in the last part, I will talk about multi-messenger constraints for dark matter interpretation of the galactic center excess, and I will spend also a few slides about other possible interpretations. So first of all, it's important to investigate if the LAT is sensitive enough to determine precisely the characteristics of the galactic center excess. And so in the first paper, we investigated this using 2 different approaches. One by using possible imperfections in the interstellar emission model, so simulating the data with one model and analyzing the data with another model. And in the top left plot, you see the reconstructed spectrum as a function of the injected one, where we try to use different interstellar emission models. And you see that there is some systematics that is of the order of 10–15%, but the spectrum is pretty well reconstructed, basically between 500 MeV, basically above 500 MeV. Then in this case, we can also investigate how the spatial morphology is well found, and this is presented in the bottom left figure, where we show the value of gamma, that is the slope of the Navarro-Franken-White, still simulating with one model, but analyzing with another model. So also this case basically tests imperfections of the model. And you see that the gamma is well reconstructed with an error between basically 5–10%. But there is another scenario that is possible where we are missing a component in our background model. For example, you might not model properly the Fermi bubbles. And so we tested this scenario by not using the inner part or the part that is closer to the galactic center for the Fermi bubbles. Then we increase the flux of the Fermi bubbles, and we see how gamma is well reconstructed. Basically, we verify that if you have any missing components with a flux at least 10–20% of the one of the galactic center excess, the spatial morphology becomes different from the injected one. So the presence of these missing components can really affect your results on the galactic center excess. Then we analyze the data in paper 2 using Bremstaluk Pi0 inverse Compton components, isotropic template, and the Fermi bubbles divided into a low and a high latitude template, and a region that is 40 by 40 degrees squared, centered in the galactic center. And analyzing the data, we find residuals of the order of 20–25%, that is similar to what has been done in the past. So the first characteristic we investigate is the galactic center excess spectrum, so also called SED. We test this with several state-of-the-art interstellar emission models. You see some of the results in the bottom left plots for different choices of the model. And the summary is presented in the top right, where you see our results with the black data and the gray band compared to recent results from Calore et al. And the previous Fermi-LAT paper on this topic. And you see that our results are roughly compatible with the others, and the spectrum has a low energy tail and a high energy tail that reaches almost 100 GeV of energy, and the uncertainty band is roughly 40–50%. Then we also analyzed the spatial morphology of the galaxy center excess, because it's important to investigate if the spatial extension of the excess is energy dependent or energy independent. And so we find the energy, basically the spatial morphology in different energy beams. We test this with different interstellar emission models. And this is presented in the two plots in the bottom, where you see the gamma value for the Navarro-Franke White as a function of energy. You see that basically the gamma is roughly constant between 500 MeV up to 20 GeV, with a value that is between 1.2 and 1.3. And this is a result that is new with respect to the past, where they investigated if there is some variation, but not with such a detail and not with several interstellar emission models. Also, the position and the sphericity is something that we need to test. So running the basically likelihood analysis with the position of the dark matter template changed at different locations in the galactic center region, we find that the position is very well centered close to the dynamical center of the Milky Way. In fact, you see in the two plots on the bottom part of the slide, this is the likelihood as a function of longitude and latitude. So a brighter color, it means that that position is preferred, and the preferred positions are very close to the center of the galaxy. Since recently, by Mathias and collaborators, there were some evidences that the galaxy center excess is not spherically symmetric. We also tested the sphericity, basically modifying the dark matter template into something that is more ellipsoidal. And so here we make the likelihood analysis as a function of the index gamma and the ratio between the two axes of the ellipse. And we find that basically this ratio is compatible with 1, with values that range from 0.8 and 1.2. So in our analysis, in my analysis, is roughly spherically symmetric. Okay, now I will spend the second part, the last part of my talk, talking about the dark matter interpretation. The first thing we have to do is basically to determine the dark matter density. We use the Salas et al. 2019 paper, where there are 3 different, basically a range of dark matter density, local dark matter density between 0.3 and 0.38. And using these 3 models and 3 different choices of the dark matter density profile that are compatible with the surface brightness of the galaxy center excess, we find 9 different scenarios for which we calculate the geometrical factor that is important for the prediction of dark matter in gamma rays. And then we label 3 models with the lowest, average, and maximum J factor that we label as min, med, max. But here we are not including any substructure. So this min, med, max, it means the minimum, average, and maximum value of the J factor for these 9 scenarios. So here we are basically finding the dark matter density using at the same time data for the rotation curve of the Milky Way and the spatial distribution of the galaxy center excess. Okay, now that we have derived the dark matter density profile or some range of possibilities, now we can fit the spectrum of the galaxy center excess, and we try a simple scenario with the branching ratio equal to 1, so a single channel. We test annihilation because the decay would have a very, very high gamma that is very difficult to interpret with n-body simulations. And in the top left, you see the summary of the annihilation cross-section and dark matter mass that fit well the spectrum with the variation of min, med, max for the dark matter density profile. Using the MED scenario, our results are similar to Calore et al. And Linden 2014. And the result is basically that for BB bar, we need something that is close to the thermal cross-section with a mass between 40 and 50 GeV. The problem of the single channels is that you fit very well the bump at a few GeV, as you can see in the bottom left figure, but then you are not able to fit properly the high energy tail above 10 GeV. To improve this aspect, we can proceed with two channels. So you introduce another parameter that is the branching ratio that is parameterized exactly as you see in the equation in the center of the slide. For these two channels, the preferred cases are mu plus mu max BB bar, tau plus tau minus BB bar. That improves very significantly the fit because, as you can see in the two plots in this slide, basically you feel some of these high energy tail being still compatible with the low energy tail and with the bump. The cross-sections values remains more or less the same as before, and basically you need that for mu plus mu minus, the branching ratio is 0.65, so most of the channel goes into mu plus mu minus. For tau plus tau minus BB bar is the opposite, so only 20% goes into tau plus tau minus, and BB bar takes the 80%. Okay, now that we have found some candidates for the gradient-center excess, we can try to see if these candidates are ruled out by dwarfs. And so we take the sample by Pace and Striger in 2018 with the uncertainties for the geometrical factor in that paper. We also test Albert et al. 2017 without finding any significant difference. We use the pipeline already used by the Fermi collaboration in previous papers. And you see in the left, the TS, so the test significance as a function of mass for the candidates that we detect with the highest significance. Among them, we have reticulum 2 that has been investigated in the past as one of the most promising dwarf. But as you can see, the stacked sample that is with the solid black line has TS that are at most 7. So since we don't have any significant signal, we can find limits for the annihilation cross-section that are presented in the right slide, in the right part of this slide, where you see the limits, 95% upper limits with the solid black line. The cyan and the green bands are for the expected limits without any signal. You see that this black line is slightly higher than the 68% containment, and the reason is due to this small TS that we find in the stacked sample between 3 and 7 of TS. Okay, now if we combine these limits with the signal from the galactic center, here I show the example of tau plus tau minus BB bar. The green data point is for the MED model, while the green box is including also the uncertainty in the dark matter density. And you see that this galactic center excess candidate is compatible with the upper limits. There are other possible interpretations for the galactic center excess, for example, with cosmic ray electrons and positrons, but these provide a signal that is energy dependent because they produce gamma rays for inverse Compton. And so in the top left, you see the gamma as a function of energy for this interpretation. So basically you have burst of electrons injected from the galactic center. These particles make inverse Compton on the interstellar radiation field and they produce gamma rays. But you expect a signal that is smaller at high energy. This is why gamma, you see with these black stars on the top left, these stars increase with energy due to this signal, and this is not what we observe in the galactic center excess data. It's also difficult to find a good match with the surface brightness data of the galactic center excess. This is presented at the top right, where I compare the data for the galactic center excess with different assumptions for the signal from electrons and positrons, and it's very difficult to find a good match for all the angular scales. Cosmic ray protons in the bottom part of the slide will create gamma rays for pi0 decay, and so the emission will be correlated with the gas in the disk, and so the emission will be elongated on the galactic disk, and this is not what we see for the galactic center excess. The pulsar interpretation is an interpretation that casted a lot of interest because of Bartels et al., Lee et al. Results using the Poissonian template fitting and the wavelet analysis. They found evidence of a faint population of sources in the galactic center region that can be compatible with millisecond pulsar in the bulge with characteristics compatible with the galactic center excess. This interpretation is basically has had an additional motivation by the papers by Mattia et al., where they model the stellar population that could be a tracer for pulsar with a boxy bulge and a nuclear bulge, and they find that these two templates are preferred over a dark matter template. But recently there were papers that casted doubts on the pulsar interpretation because they used simulations, and they saw that the non-Poissonian template fitting can misattribute to point sources the dark matter signal. And then Zhong et al. 2019 redid a wavelet analysis with the 4FGL, and they did not find any significant evidence of these faint point sources. So to conclude, we still have to do a lot of work for the dark matter interpretation. In this table, I summarize the characteristics for the different interpretations. One of the main things where we have to work more is on the smoothness of the galactic center excess. So if the galactic center excess is something diffuse or something that is more compatible with the point-like scenario, and this will help, for example, into disentangle between the pulsar and the dark matter interpretation. The electrons and positrons seem to fit not very naturally the morphology and the spatial distribution, but maybe using some more complicated model is still possible to fit the galactic center excess. So more work has to be done, so stay tuned.